consumption. Okay, guys, let's continue again on the principal strain, strain quadric invariants, volumetric and deviatoric strains, cubical dilatation principles. So the principles of all of these uh, concepts, no, as introduced on the analysis of stress, is actually the same. No, I will use the word the same because the formula are really equivalent in terms of the expression. But of course, the interpretation is no longer on the stress aspect, but now on the strain aspect. And some variables were only changed to signify that we are now talking of strains rather than stresses. So for the principal strains, we know that the equation can be derived using the eigenvalue equation. No? So we refer to the eigenvalue equation for strain. So the eigenvalue equation for strain is the same as that with your stress. Okay, so this is simply a lambda or a sigma in your stress, and these are the invariants. Okay, so I1, I2, and I3 are the invariants equivalent to Lii, or simply the trace, and this is the 1/2 of the Lii Ljj minus Lij Lij, and the determinant of L. Okay, so if you have an Eulerian, you just change this to letter E. Okay, so there's no problem with changing your strain on the aspect from where it is derived, no? So from what particular description it was derived. So the strains quadric is the same, no? Lij cassis of I cassis of j is simply k squared, and the volumetric and deviatoric strains are still the same, no? This is an Lij minus Lkk over 3 delta ij, or if you're using the Eulerian, it's an Eij Ekk over 3 delta ij. The cubical dilatation was not uh, emphasized on the stress analysis, since dilatation has something to do more on strains rather than stress, and simply this has something to do with the sum of the normal strains, which are the components on the diagonal term of your strain tensor, which is simply Lii, or simply the first invariant, no? So this is simply Lii. So this is simply L11 plus L22 plus L3. So in your examinations, I will just, if I ask these things, you simply get your calculator and add it, no? So I will not give you a question that cannot be solved within if it can be solved within a few seconds. So I will only be giving you more than a few seconds. So my multiplier is about 2 to 3. No? If I can solve it in 1 minute, I'll give you maybe 2 minutes or 3 minutes to solve it, just to be fair. Okay, so that's how I deal with examinations. So for the right stretch tensors, which was not discussed on the above uh, principles, or the above lecture on stretch ratio. So this is another way of trying to determine the measurement of your uh, linear strain, no? In terms of stretch. This is now this is no longer the stretch ratio, but rather the actual stretch when you say right stretch, you are actually referring to the green uh, description, which has something to do with the Lagrangian. Okay, remember that G is related to the Lagrangian description. And take note that your right stretch is simply given in terms of your SII, where SII is simply the sum, okay, of the diagonal components of your stretch. And this, of course, is related to the square root of your GII, where if we want to take a look on the uh, explicit definition in mathematics, so this is simply an s squared equals g. Therefore, an s is equal to the square root of g. So if we let q be the principal directions n1, n2, and n3 obtained in the basis of doing the same procedure as that with the principal stress directions, or when we refer to the analysis of stress, then we can come up with the value of your q in terms of the principal directions. And take note that q can be expressed now in terms of the three principal directions. So this becomes now a matrix. Okay, so because n1, n2, n3 are vectors of 3 components, therefore this is a matrix of 9 components. And if we let lambda squared be the principal values of G, okay, obtained by using again the principles which are the steps, the procedure we have done in the analysis of stress, then we can come up with G as the product, no, of your Q transpose lambda squared times Q. Taking note that if we equate now your S, a square root of G, after solving G, we just take the square root of this, we can now solve for the right stretch or the green description of your stretch. So this is another way of measuring again the value of your linear strain tensor in terms of stretch components. So it is very important that you convert or you get the value of G in terms of the principal values. Okay? Because if you are not, if you will not use the principal values, then your right stretch will not be the same. The value obtained will not be the same with that when you use the principal values, because the off diagonal terms on the matrix of G will not be zero. Okay, so that is a very important thing to consider when you are solving for the right stretch. So I'll see you on the next video to give you one example on the analysis of strain. Thank you very much for listening.